Imagine being a human who leaves Earth, looks back at it hanging silently in the black void of space, and realizes that every war, every border, every human story ever told exists on that fragile blue sphere beneath your feet. Because that is exactly what Neil Armstrong experienced when he became the first human to step onto another world. Not as a fictional hero, not as a movie character, but as a trained engineer, test pilot, and scientist whose journey into space was built on real physics, real danger, and real research that forever changed humanity's understanding of the universe. Neil Armstrong was not born an astronaut. He was born in 1930 in Ohio, fascinated by flight from a very young age, earning his pilot's license before he even had a driver's license, and later studying aeronautical engineering at Purdue University, where he learned the mathematical and physical foundations that would later allow him to survive some of the most extreme environments humans have ever entered. Before space, Armstrong was a naval aviator and then one of the most skilled test pilots in history, flying experimental aircraft like the X-15, a rocket-powered plane that reached the edge of space and exposed him to hypersonic speeds, extreme G-forces, and near-fatal situations that demanded perfect understanding of physics rather than instinct alone. These experiences were not adventures, they were scientific tests designed to push the limits of human flight, and they trained Armstrong to remain calm when systems failed, data disappeared, and survival depended on rational decision-making. When NASA selected him as an astronaut in 1962, space exploration was still in its infancy, filled with unknowns about how the human body and mind would react beyond Earth's atmosphere, how spacecraft systems would behave in microgravity, and whether humans could even function properly outside Earth's protective magnetic field. Armstrong's first space mission, Gemini 8, nearly ended in disaster when a thruster malfunction sent the spacecraft into a violent spin, rotating once per second and threatening to render both astronauts unconscious. Armstrong diagnosed the problem in seconds, shut down the system, and stabilized the spacecraft, a decision that saved their lives and provided NASA with critical data about spacecraft control failures and human response under extreme stress in orbit. This incident alone reshaped NASA's engineering protocols and astronaut training, proving that human decision-making was not a weakness in space, but a necessity. By the time Apollo 11 was launched in July 1969, the mission was not just a political milestone, but a massive scientific experiment involving thousands of engineers, physicists, geologists, and medical researchers, all focused on answering fundamental questions about the moon, space travel, and human survival beyond Earth. When Armstrong, Buzz Aldrin, and Michael Collins left Earth aboard the Saturn V rocket, they entered an environment where gravity no longer anchored the human body. Fluids shifted toward the head, muscles began to weaken, and bones slowly started losing density, phenomena that astronauts carefully documented so scientists could understand how long humans could safely remain in space. As Apollo 11 traveled toward the moon, Armstrong observed Earth shrinking into the distance, later describing it not as a dramatic sight, but as a scientifically humbling one, emphasizing how thin the atmosphere appeared and how fragile Earth looked when viewed without borders or scale, a realization that influenced environmental science and planetary studies for decades afterward. When the lunar module, Eagle, separated from the command module and descended toward the moon's surface, Armstrong was not seeing a mythical landscape, but a geological one, identifying craters, boulders, and surface textures that scientists had only theorized about based on telescopic observations. During the final descent, the onboard computer became overloaded with data alarms, a real engineering issue caused by radar processing limits, and Armstrong again took manual control, steering the module away from a dangerous boulder field, landing with only seconds of fuel remaining, a moment that combined human skill with scientific understanding rather than luck. When Armstrong stepped on the lunar surface and spoke his famous words, it was not a poetic exaggeration, but a literal scientific truth, a single human step representing thousands of experiments, calculations, and research hours conducted across multiple disciplines.
On the moon, Armstrong did not simply walk. He conducted structured scientific observations, documenting how lunar dust behaved, how gravity affected movement, how shadows appeared sharper due to the lack of atmosphere, and how the surface responded to pressure, providing invaluable data for planetary science. He and Aldrin collected rock and soil samples that later revealed the moon's volcanic history, age, and relationship to Earth, confirming theories that the moon likely formed from debris after a massive collision early in Earth's history, a hypothesis now known as the giant impact theory. Armstrong also placed scientific instruments on the moon, including a seismic experiment that detected moonquakes and meteorite impacts, proving that the moon is not geologically dead but still experiences internal activity. One of the most important contributions of Apollo 11 was not technological, but biological, as Armstrong and his crewmates were quarantined after returning to Earth so scientists could study whether lunar material posed any biological risk, a precaution that showed how little humanity truly knew about extraterrestrial environments at the time. Armstrong consistently emphasized that space was not a mystical realm, but a physical one governed by the same laws of physics, stating clearly that the moon held no evidence of life, structures, or anomalies beyond natural geology, dismissing conspiracy theories and reinforcing the importance of scientific evidence over speculation. After Apollo 11, Armstrong did not capitalize on fame. Instead, he returned to academia, teaching aerospace engineering and contributing quietly to research on flight safety, space policy, and accident investigation, including the Rogers Commission that investigated the Challenger disaster, where his input helped identify engineering failures rather than assigning blame. Armstrong frequently spoke about how space travel revealed the limits of human perception, explaining that space does not feel large when you're inside it, but rather empty and silent, and that the real psychological impact comes from isolation, reliance on systems, and the awareness that survival depends entirely on engineering and teamwork. He rejected exaggerated claims about seeing stars differently or experiencing supernatural phenomena, explaining that stars are harder to see in space due to bright sunlight and reflective surfaces, a detail that aligns perfectly with optical physics. Armstrong also addressed the question of fear, stating that astronauts were not fearless, but trained to manage fear through preparation, data, and procedure, reinforcing that space exploration is a discipline of science, not bravery alone. He acknowledged the dangers of radiation, micrometeoroids, and system failures, emphasizing that every mission carried calculated risks based on extensive research rather than blind optimism. Armstrong believed that human expansion into space should be gradual, sustainable, and driven by scientific value, not spectacle, advocating for robotic missions alongside human exploration to gather data efficiently and safely. His observations helped shape future missions, including the development of space stations where long-term studies of human physiology in microgravity became possible. Armstrong often reflected on how seeing Earth from space changed his perspective, not spiritually, but scientifically, highlighting how Earth's climate systems appeared interconnected and delicate, influencing later environmental monitoring programs that use satellites to study weather, ice loss, and atmospheric change. He supported international cooperation in space, believing that scientific knowledge transcends national borders, a philosophy reflected in modern collaborations like the International Space Station. Until his death in 2012, Armstrong remained committed to factual accuracy, rarely giving interviews and always correcting misinformation about space, emphasizing that exploration is a process of learning, not myth-making. His legacy is not just that he walked on the moon, but that he returned with data, samples, and observations that permanently expanded human knowledge of planetary science, orbital mechanics, human physiology, and engineering under extreme conditions.
Neil Armstrong's journey proves that space exploration is not about heroes conquering the unknown, but about scientists carefully stepping into it, measuring, observing, and returning with truths that reshape our understanding of the universe. And as humanity looks toward Mars, deep space, and beyond, the real lesson Armstrong left behind is not his footprint on the moon, but the method by which he placed it there, through education, discipline, evidence, and respect for the laws of nature, reminding us that the universe does not yield its secrets to imagination, but to science, patience, and the courage to face reality as it truly is.
If you want more such knowledge, then subscribe our channel.